The law of conservation of angular momentum says that for a closed system, the angular momentum of the system is conserved. And what that means is that the final angular momentum must equal the initial angular momentum. In a previous lesson, we learned that angular momentum was the product of moment of inertia times angular speed, so the final product of those values must equal the initial product of those values. A system changes its moment of inertia, and when it does that, it will change its rotational speed. Let's try a couple of examples. In the lower left here, we have a diver in a tuck position. He has a relatively small moment of inertia because most of his mass is relatively close to the rotational axis. You can see how he's pulling his legs in, even curling his toes in an effort to get as much of his mass as close to the rotational axis as possible. These ice skaters are doing the same thing. They're pulling as much of their mass as possible as close to the rotational axis as they can. When the diver comes out of the tuck position before entering the water, they stretch out as much as they can. You can see that this young lady is even pointing her toes to get as much of her mass as far away from the rotational axis as possible, which gives her a much larger moment of inertia. Well, when the moment of inertia goes from small to big, what must happen to the rotational speed in order that that product of moment of inertia and angular speed be the same? The angular speed must decrease. This is why divers get into a tuck position, because they want to spin as quickly as possible, and then when they enter the water, they don't want to be spinning as much, so they stretch out. That's the law of conservation of angular momentum. Same thing for ice skaters. When they come out of this spin, they stretch way out. Stretch the leg out, stretch the arms out. That makes more of the mass farther from the rotational axis, which increases the moment of inertia. And if the product of moment of inertia and rotational speed must be the same, that means that when they come out of the spin, they have a much lower rotational speed, and you're much less likely. Here are a couple of other examples. You might have seen a spiral wishing well at a museum, and you can roll a penny in here, and when the penny is going around the outside, it has a rather large moment of inertia, and it has a rather small rotational speed. As it spirals towards the center, there is a much smaller moment of inertia and a much higher angular speed. Same thing with comets going around, let's say, the sun. When the comet is far away from the sun, you can consider it to be a point mass, and it has a rather large radius from the sun, so its moment of inertia is quite large, which means its rotational speed must be rather small. As that comet comes close to the sun, it has approximately the same mass, but its distance is much, much smaller, which means its rotational inertia is much smaller, which means that its angular speed must be much, much larger. It's going to whip around the sun as it gets closer to the sun. And here we have a person sitting on a chair with a couple of bricks, and here the rotational axis goes up and down through this person, and most of the mass is relatively close to that axis, so the moment of inertia is relatively small. When the bricks are held out, more mass is further from the rotational axis, so the moment of inertia gets larger, and if this individual is spinning on the left, he's going to spin rather quickly. When he moves the blocks away from his body, because his moment of inertia increases, his rotational speed is going to decrease. All of those are examples of the law of conservation of angular momentum.